Hello, and welcome to another episode of Oxford Online Maths Club. My name is James, and today I'm joined by Joanna.
Hello.
So Joanna's one of our students. We're going to be talking about differential equations, but first I want to say hi to people in chat who are here. Hi to Tia and Raphael and Amelia, Ali and Darishle, Abikar's here as well. People are saying hi in chat as well. If you've just joined us live for the first time, then hi! Welcome to the Online Maths Club. Welcome to the event. If you're watching live, you can join live chat over at slido.com/OOMC. Also, link on the Maths Club website. If you're joining us because you saw something at the Oxford and Cambridge Student Conferences, I spammed the link to this quite a lot at that event, so maybe somebody here is here from that. Cool. Iwana, do you want to tell people about you're a current student? What year are you in? What college are you at? That sort of thing.
Sure. So my name is Joanna, and I am a second year student. I'm at St. Anne's College, and I'm an international student. I come from Romania, and yeah, that's about it.
Cool. Okay. I think. Oh, my computer's not happy, but I'm supposed to not say that out loud because it's a curse. I think we should jump straight in and tell them about differential equations. They've got excited for differential equations because I accidentally advertised it as happening last week. People arrived very excited for differential equations last week, and I had to admit, oh no, sorry, last week it was just me doing some weird maths problems, but this week actually differential equations. So I'm going to hand over to Joanna to introduce what differential equations we're going to be talking about and what we're going to be doing to them. Over to you.
So today, I want to talk to you about hanging chains and their shape, which doesn't sound that exciting at first, but honestly, once we realize that we can actually model them with differential equations, it all becomes way more exciting, and I'm gonna need you to trust me on this one. So basically, the premise that we're gonna start on is, what does a hanging chain have in common with, say, how the sound of the strings of a guitar travels, or with the position of a single electron particle at a given time? Well, at first glance, obviously, there's probably nothing. They all seem like things coming from very, very different worlds. The first one is just something that you see in your everyday life. The second one is related to art, while the last one seems like just some physics stuff. Well, keep this question in mind, and I bet that I can convince you in, say, 15 minutes that they are actually incredibly, like, surprisingly similar things. So I would suggest to think firstly about a hanging chain and to consider its shape. We can find many different hanging chains or hanging strings in our daily life. So I think that you can actually see these every day on your way to school, or actually whenever you take a walk, you can see them outside quite everywhere. So when a string has its two ends fixed, the gravity will bend it into a very nice convex curve. So do you think it's possible to find out the precise expression of this curve? It looks somewhat like y equals sine x, or maybe it is closer to y equals x squared. Well, this is quite intriguing, and this is our starting point. Let's see if we can actually derive any mathematical results about this curve. So the first thing that we actually need to do whenever we encounter some of these physics problems is to draw a picture. And oh god, this is a very random line there, but whatever. So the first thing that I want to do is to take some axes and draw this interesting shape. So say that these are our axes, and let's say that we've got these as our hanging chain. And now, to make our lives easier, let's assume that we have a very thin and inextensible chain that hangs stationary in the air. So what we can see from real life pictures that we should have in mind, or from James' picture, is that a hanging chain has a lowest point. So is this one. And let's label this A because it will be pretty useful later on. So one point is kind of boring to have though. because we cannot really do anything with just one point. So let's just choose another arbitrary point B, and let's put this right here. So now we can consider the chain AB. We have some forces acting on the chain AB. So let's just identify them. There is a horizontal force F that's acting on the left of A right here. If I can actually make this look horizontal.
Ooh.
So it's something like this. This is F. Then we've got a tension in the string that we will very conveniently call T, that is acting on point B along its tangent. So it's just here. And clearly we have the gravity of the chain AB. So we end up with a diagram that looks like this. And now clearly the chain AB is hanging stationary in the air. So the resultant force is just zero because nothing is actually happening here. Then T is the only force that is not in either the vertical or the horizontal direction. So we can just simply decompose it into these two directions. And we can do that somewhat like this.
This is resolving forces, I think is what it's called on A level. Sure. Clear if they've seen resolving forces in mechanics. I think they've seen it for things sliding down hills and sort of things at an angle. Here, the chain, or bit of string, or whatever it is, the chain has a kind of built-in angle that bit of chain is at an angle. So the tension is acting, pulling along the chain. That tension is acting at an angle, which you've just called theta. Aha. Okay.
And then we've got that this horizontal component would be T times cos theta, and the vertical component will just be T times sine theta. And there we go, all of our forces are just in either the horizontal or in the vertical direction. And hence we obtain a system of two equations, which is just solving firstly in the horizontal direction. It is just F equals T times cos theta. And then looking at the vertical direction, this is just G equals T times sine theta. And we've got this system that we need to solve in order to find our required equation. So what we can do with these two equations is we can divide them and rearrange them and see what we get. And so if we divide them, we get that T times cos theta over T times sine theta. Actually, I'm gonna divide the second one by the first one, just because it looks nicer. So if we do that, we get tan theta rather than the cotangent of theta. So yeah, dividing them, we get tan theta equals G over F.
Okay.
But now applying our usual formulae, we get that G, which is mg over F, and we can express this as rho times L times G over F, which I'm going to denote by L.
Hang on. That one's going to need a bit of an explanation, sorry, for the rho.
Yep.
I know what rho is because I work in fluid dynamics. And in fluid dynamics, rho is density.
Sure.
But here it's not quite... Is it density? I guess your chain has got... It's got kind of a mass per unit length of chain or something. So
yeah,
I guess
it is actual density, but
okay.
Probably not in the way that is defined in fluids.
Right. Okay, so this is density. I guess rho times L the length. That's your mass. Okay, so that makes sense to me. I guess that the mass of that bit of chain between A and B. I'm gonna colour it in. The mass of that bit of chain between A and B has got some weight, m times g, which depends on the kind of density of chain and also on the length of that bit of chain. Using density for a one-dimensional thing it feels a little bit strange, but yeah, I guess that's all good. Someone in chat, Ali would like mu for mass per unit length, also acceptable. Doesn't really matter which Greek letter you use, but that's all right. And there was a question. Sorry, I'm keeping an eye on chat. There was a question as well about why is that F horizontal? Can you remind us why F at the bottom is horizontal?
So we can think of F as the tension in the string at point A. And the tension in the string will quite always be tangential to the curve. And if we consider the tangent at the point A, which is the lowest point on our plot, it would just be horizontal because we've took A to be on the y-axis. And so the tangent to the curve at A would just be horizontal.
I'm trying to think of a good way to explain why the tension is always tangential. I guess if it isn't tangential, then the thing deforms so that it is, which is not a very good explanation. But hey, I guess in my chain of paperclips, I found this chain of paperclips, by the way, just on my desk. In this chain of paperclips, each paperclip is kind of touching the next one, and they're pulling along, and that force is kind of tangential to the line of paperclips along there. So at the bottom, the tension at the bottom is pulling. It's a horizontal thing. It's pulling. It's feeling the force of being pulled from the other bit. What are the symbols in the numerator over F in the third equation? I think that's an M for mass and a G for gravity. Sorry, I'm now keeping up with chat. I think we're now up to date with chat. Sorry to interrupt. You've got down to tan theta, something we don't know because we don't know the shape, is L over A, where L is the length of that bit of chain and A is some number to do with how heavy metal is and what that force at the bottom is. What's the plan? What's going on?
Okay, so here what I've done is I've just put all of my constants into this number A. So basically A here is just F over rho times G. And now M here was the mass of the chain, then rho was the density of the chain, L is the length of the chain, and G is the gravitational acceleration, as James said. So F, rho, and G are all known quantities because they depend just on the material that the chain is made of, and obviously the gravitational acceleration is constant everywhere, and hence this A is just a known quantity. So we actually know what this A is. And we can just treat it as a constant in our next calculations because it is just a value that we know. And so we've got to this point that our whole system of equation just reduces to this equation, which is that tan theta is L over A. But now, how can we find something about tan theta? Well, we can see from the picture that tan theta is tangent to the curve. And hence we can write it as tan theta being equal to y prime, which is exactly a tangent to the curve. And we also know from the above that tan theta is L over A. And hence we obtain the differential equation y prime is L over A. And now the only thing in this equation that we still do not have an expression for is L, which is the length of the chain AB. And this is what we're going to do next. We're going to obtain an expression, a mathematical expression for this length of the chain. And in order to do this, what I'm going to do is we're going to consider a very, very incredibly small and short length DC of our curve. As it is extremely short, we can approximate it to a straight line. And if we have straight lines instead of curves, we can apply the simplest, lovely Pythagorean theorem. And applying this, we simply get that dc squared is just dx squared plus dy squared. Because all of these are just incredibly small quantities that I've labeled by dc, dx, and dy. And the thing that we need for the differential equation is the value of dc over dx. And so rearranging this to get dc over dx, we simply get that dc by dx is the square root of 1 plus dy by dx squared. And now what remains to be done is to integrate both sides in order to get our final result. So if we integrate this between 2 points AB, say, we obtain that the integral of AB of 1 dc is simply the integral of AB times the square root of 1 plus dy over dx squared times dx. And so let's take a step back and consider this equation, because just looking at it, it seems quite unphysical, but actually it's got a physical meaning. So what we have just shown is that the length of the chain between two random points, A and B, is just this integral. So it is just the integral between A and B of the square root of 1 plus dy by dx squared dx. And hence, using this, we can obtain the length of the whole chain, which is simply L. So using this expression that we have here, we get that the length of the whole chain is simply given by L, which is the integral between 0 and x of the square root of 1 plus dy by dx squared dx. And using just to keep our notation constant, then we can rewrite this as the integral between 0 and x of the square root of 1 plus y prime squared dx. And now I can see that there are a bunch of questions in the chat.
It's okay.
See, so, yeah.
We've gone quite quickly through that derivation, but it's, I think, worth stressing that I guess the reason that it was quick for you is maybe because it's come up in different places or something, that this has come up in other places as well, because this integral, the thing you integrate is square root of 1 plus dy by dx squared. No. That's what you integrate to find the length of a curve. That works whatever your curve is. Nothing to do with hanging chains, nothing to do with mechanics. If you've got a curve like sine x or something, and you want to find out how long sine x is, then the thing you need to integrate is you need to integrate the square root of 1 plus dy by dx squared, all square rooted. That's the thing you integrate between, I don't know, wherever you want to go, 0 and 2 pi. If you know about integrating sine x and functions involving sine x, then you can maybe go and try and do that integral, who knows, and find out how long is a sine curve. Just not a question but that I'd ever thought about in school, I guess, really, because I was so busy learning how to integrate and differentiate sine x, find the area, that I never thought about finding the length of sine x, I suppose. Works for all functions, I suppose, that you can work out dy by dx for. And it's come from Pythagoras. It really is Pythagoras. This thing that you wrote down of dc squared, for the little change in what was going on, being dx squared plus dy squared. I'm going to draw a tiny picture for that. If you imagine a chunk of your chain or curve or whatever it is, maybe this is a little zoom in on a tiny bit of sine x, like just in here, a little zoom in on what's going on over there, then you want to know how long the bit of sine x is, because my task is to work out how long sine x is, or work out how long the chain is or something. So maybe dc is the notation you were using for how long that little bit is. And by Pythagoras you can just write it out as dx squared plus dy squared, square rooted. And then some rearranging to say, aha, that gives me a differential equation, integrate it to work out how long this thing is. Integrating just means adding up lots of the contributions. Is this university maths or A-level maths or A-level further maths? There's someone in chat. What do we think? So not A-levels because Romania, right? But
no A-levels, yeah.
Did you do anything like this in school, or is this something?
I mean, we got quite far into the integration bit, but we did it more from a pure maths side of things. So we've done quite a bunch of pure maths analysis stuff, but we never actually saw quite what everything means physically. So not quite this, but yeah.
I'm trying to remember if I think this equation, this expression for if you want the length of a curve, like sometimes it's called arc length. I'm not entirely sure why. Arcs for me means something to do with circles, but hey, here, if you want the length of a curve, then you're supposed to integrate the square root of 1 plus the derivative of y squared. I think that equation might have turned up for me at some point. It was in a formula booklet or it was told to me in further maths, but it's not something I really thought about a lot, except that I thought about it a little bit in terms of exactly hanging chains, because somebody showed me some hanging chain stuff when I was in school. Somebody's asked, why do we need to worry about negative numbers? We've got a square root. Sometimes we worry about taking square roots of negative numbers. I guess no, the thing inside here is not negative because it's 1 plus something that's squared. When you square that derivative, you get something that's safely positive. Adding 1 to it, very safely positive, so we're okay. And one question for why is the integral from 0 up to x, which I guess is because really Joanna wants to talk about the length of this pink bit of chain between A and B. That's the thing we thought about forces for. Thought about what the forces were pulling on the left where it meets the other half of the chain and pulling at the top where there's some tension in the chain. We thought about the forces on that bit of chain. And gravity there depends on how much chain you've got, which depends on the length of that bit. So that's why it's the integral from 0 up to, I guess this is some point x. Okay. Nice. You've got to, I'm pausing a bit because we're about to have some solving differential equations. But I guess you've now got to a differential equation, right? Because you've got something like y prime, the derivative of y, you know, is related by your force balance, is related to L over some constant A. And you've got an expression for L. Do you want to outline, before we jump in and do the calculation, do you want to outline what happens next, or what we're trying to do?
Sure. So we've got these two things that are our most important things that I think we've got throughout this whole proof, because from now on it's just a matter of solving differential equations, so it's nothing quite as important as what we've got here. So the first thing is our that we've got is our definition, sort of y prime, which is that y prime is L over A. And right here above, we have this expression for L, that L is just this integral. And so we can put these two together to get our final differential equation, which is going to be that y prime is just 1 over A times this integral, so the integral between 0 and x of the square root of 1 plus y prime squared of dx. And now, basically, then our next steps would be, well, firstly, we don't really like working with integrals because they're much harder to work with than derivatives, say. And so the first thing that we will like to do is to get rid of this integral. And then after that, we will just see that it's just a matter of using a substitution and then just basic separation of variables. But we will see that whenever we solve differential equations, we have some constants, especially, so we've got some constants, either when we integrate stuff or when we solve differential equations. There's always a plus c or an a times x, say, where a is a constant. And what we would like in order to have a precise solution is to get rid of these constants. And so we will also worry about finding a specific value for these constants. But let's firstly just get rid of this integral here. So we know that, roughly speaking, integration is just the opposite of differentiation. So we can simply take the derivative of both sides here, and this will lead us to y double prime being equal to 1 over a times the integral between 0 and x of the square root of 1 plus y prime squared dx prime. And here, noting that, again, integration is just the opposite of differentiation, we see that this is just 1 over a times the square root of 1 plus y prime squared. And now we have simply reduced this problem into one simple differential equation that we can easily solve using just A-level techniques. And this is quite wonderful because we've got from a physical problem, something that we see in our everyday life, to a differential equation that looks fairly abstract, but it is quite easy to solve. So I can see on the chat that there is a question about boundary conditions, and that's exactly what we're gonna do. But this is just what I was talking about with the constants. And basically, the boundary conditions will allow us to find values for those constants. But firstly, we need to solve this thing and get the result in terms of those constants, if that makes any sense. But it will soon, even if it doesn't right now.
We're going to solve it nice and carefully in kind of lots of in a general sense, and then think about applying some conditions afterwards. Harriet wants to know why the 1 over a. I think the 1 over a stays there, Harriet, because it's just a constant out the front. The left-hand side, when you differentiate the left-hand side, you should definitely get second derivative of y. That should definitely work. And then on the right-hand side, well, differentiating the integral is pretty hard. Apparently it gives you this thing. But the 1 over a is just it's multiplied by. It's like 3 times x rather than being like 3 plus x. So it's a constant multiple of some stuff. And it hangs around because that's what constant multiples do. And Nico Hulkenberg's here, so that's nice. Current substitute Formula 1 driver. Possibly, definitely last week, possibly next weekend. Chat lets you set your username to whoever you want to be. Cool, right, okay. We've got a second order differential equation. I've remembered that in A-level, I only learned about second order differential equations quite late on, and I only learned about them with constant coefficients, only having pretty straightforward differential equations with 2 derivatives in. This one's got square roots and it's got squares and it's got so many things going on. It's sort of surprising that we don't give up now, right? We can. I know what you're going to do next, but I think it's worth stressing just how weird this is that we don't have to give up now. Lots of research problems with differential equations. You get down to a differential equation, and that's great news because now we can give it to a computer to go and solve it. We can get the computer to just, brilliant, computers can just kind of have a go at it. Whereas here, you don't have to give up and give it to a computer. You can actually solve it. I'm going to shut up and let you actually solve it. Go
on. So basically, we can reduce this to a first order differential equation quite simply. So we note here that we only have the second and first order derivatives of y appearing in the equation, while y doesn't appear on its own at all. Hence, let's just simplify this by letting some variable p be equal to y prime. And hence, this differential equation simply becomes dp by dx being equal to 1 over a times the square root of 1 plus p squared, where p again is just y prime. And now, what's the simplest method of solving differential equations? Well, it's just the classical separation of variables. So to do that, we see that we can rewrite this as dp over the square root of 1 plus p squared, which is just equal to dx over a. And integrating both sides, this simply gives the integral of dp over the square root of 1 plus p squared being equal to the integral of dx over a. Or equivalently, the integral on the left-hand side is simply one that appears in A-level textbooks. It is just a formula, basically, that we all had to memorize. It is just the inverse hyperbolic sine of p. And the integral on the right-hand side is just x over a plus c, where c here is just a constant. And now, we obviously don't really want to have a constant in our answer, as this will not give us a satisfactory answer. It will not give a nicely written expression for a curve. So we need some conditions that we can establish from just the physics of our problem that will give us some information, allowing us to determine the value of this c. So what information should we have in order to determine c? So, well, know that the value of p at some point will help us enormously here. So now remember what p actually represents. P was just equal to y prime. And hence, we can just think about the physical meaning of y prime. Well, at x equals 0, we see that the corresponding point on the y-axis was just a, which we know is the minimum or the lowest point of our curve. So what do we know about the derivative of the minimum? Well, it is simply 0. And hence, what this means in mathematical equations is that y prime of 0 is just 0, which we've established by looking at the lowest point of the curve, which was a. Or equivalently, using our notation and our substitution of p, we see that this equivalently is just p of 0 being equal to 0. And putting this into the differential equation above, we find that we must have that hyperbolic sine to the -1 of 0. It should be 0, which is 0. This should be just 0 over a plus c. And from this, we clearly obtain that very nicely c equals 0. And then our differential equation simply becomes hyperbolic sine to the -1 of p being equal to x over a. And because inverse functions do not look that nice on paper, this just means that p equals hyperbolic sine of x over a. And now recalling that p was just y prime of x, we see that this just means that we've reduced the problem to another differential equation, which is just y prime of x being equal to hyperbolic sine of x over a. And this is now the differential equation that we need to solve. And again, we can simply just use separation of variables. And actually, we know that they are already separated. So we just need to integrate both sides, and we're going to get our final results. So integrating both sides, we get that dy by dx is simply the hyperbolic sine. Oh, sorry, this is our equation written more explicitly. And integrating both sides, we obtain that the integral of 1 dy is just the integral of hyperbolic sine of x over a dx, which gives our general solution for the equation of our curve. So the right-hand side is, again, an integral that appears in A-level booklets. Is just an integral that we know, that we need to memorize, basically. And the integral on the left-hand side is very simple. It is just y of x. So after integration, this gives y of x being equal to a hyperbolic cos of x over a plus another c, which is another constant that we have after integration. Yeah. Should I pause, or are there questions?
I guess, well, you've got down to a solution. So this is a good point. I think you've got a couple of constants in there, but I think it's amazing that you can solve this. And I'm calling this solved because we've now got down to a statement that says y equals. I'm feeling a bit sorry for chat because it's a miracle that we can solve this. Really, it's kind of impressive that we can solve it. Along the way solving it, you've used some hyperbolic functions. Now, some people met hyperbolic functions a couple of weeks ago when I did quite a confusing live stream that included some hyperbolic functions. That was really confusing, and 2 weeks ago. Hopefully everybody's forgotten about it. It was that bad. But some people might have learned about hyperbolic functions in A-level. If you haven't learned about hyperbolic functions, then basically everything on this screen at the moment is probably not something that you can follow along with in the same way as maths you've seen before. But the kind of shape of what's going on, I hope, feels kind of sensible, that there's something we don't understand, there's a differential equation at the top, and then by invoking some sort of special functions or knowing how to do some integrals and knowing how to solve some integration like this for some pretty complicated things, we can get down to a final answer. I think even if you've never seen any hyperbolic stuff before, then hopefully something like this, the kind of story of what's happening, can still work through. Why did we use hyperbolic sine for the integral instead of tan? Is because of this square root in here. The integral, so at some point in A-level you learn that you learn how to do this integral. At some point in A-level you learn how to do this integral, and much later in, I think, further maths, you learn how to do this integral. And these look quite similar. This one's got a square root in it, but they've got completely different answers, just completely different functions. They're actually extremely different in terms of their behaviour. So it's kind of amazing that we can get down to this solution just by Joanna knowing lots of integrals. If you haven't seen hyperbolic functions yet, which I imagine is almost everybody watching hasn't seen hyperbolic functions yet, remembering that we're forgetting about the time I mentioned them 2 weeks ago. If you haven't seen hyperbolic functions yet, then I guess you can have this as something to look forward to for A-level further maths or equivalent, that at some point in A-level further maths, you will learn how to do integrals like this, and integrals like this, to get down to solutions to even more different things. We've got a solution. Yeah, so Taylor says, are we going to go over hyperbolic functions in any of these sessions? Which is good, that's evidence that people have forgotten the time that I tried to explain them 2 weeks ago. It's good, it's working. I don't do, so hyperbolic A-level further maths or equivalent, so yeah, okay. Harriet's maybe done them in year 12, and Nico Hülkenberg has got a useful link. Thank you, Nico Hülkenberg. Always helpful, Nico. So a link to some formula booklet. It's formula booklet from the olden days because A-levels, I think, don't have formula booklets anymore. Or maybe they do this year. It's all very complicated these days. I say formula booklet quite a lot because it's what I had at school. Did you have a formula booklet at school as well? Like a booklet of answers?
No.
Okay, so
no,
you had to learn it.
No.
You had to learn everything, right? You had to actually know this.
Yep.
Right.
Yep.
And I guess people watching, doing A-levels these days, they've got to actually learn these. They've got to actually know them. Whereas back in the day, people like me would just look them up in this booklet that I've just found on my desk. My desk is great today for finding things. It's got all these different facts in it that I didn't have to learn. Who knows? Right, cool, good. They still do, says somebody. Okay, maybe they still do have formula booklets. They still have formula booklets. They're great, aren't they? I just threw mine on the floor. Right, maybe, okay. I've misread some news. People do have formula booklets. Okay. I don't know why I thought people didn't have formula booklets. Have a great time with your formula booklets, everyone. That sounds lovely. We've got a final answer out. I've just called up Desmos, because we've got down to a shape. You're going to tell them about the constant, I think. But first, before you tell them about the constant, I've got... This is what the hyperbolic cos function looks like. So I've just put in that final answer. How do you move around in Desmos? Oh, there you go. Okay. And the way that A and C behave are just transformations of the curve, which I guess makes sense that so far you've been thinking about the shape of a hanging chain, but nobody said where it is. Is it up here or is it down here? And also, so far we haven't really thought about the shape like this. So this is another graph transformation that's doing some stretching. Kind of looks quite fun. Like that. Oh, I can do upside down chains. I hope A is not negative. Okay. It's not how upside down chains work. Not a thing. I think we've done alright. If I hold this here, put that on the screen, looks pretty good. You know, maybe choose A and C to make that be a good matchup. Good. Okay. Sorry, you wanted to tell them about constants, maybe?
Yeah. Yep. Just one more step and then we're done, I guess.
Sorry.
So, basically, what we want to do is we want to get rid of the C. We want to just have a numerical value for it. And in order to get rid of it, we need a value of y at some point. And the simplest we can get is a value of y at x equals 0, because 0 is literally the simplest point that we can think of. And we know that it would be nice to have y in the simplest form possible. And to do this, we would like to have c equals 0, so just completely getting rid of c. And to do this, we can simply assume that y of 0 is a. And we can just use this to get rid of our constant. And why can we do this? Well, we can simply let y of 0 being to be equal to a, because we have no further restrictions on the initial value of y. So why not just make our lives easier? So this gives, as we wanted, y of 0 being equal to a times cosh 0 over a plus c, which is simply equal to a. And so c is just 0, as we wanted. And hence the final expression of our curve, the equation of the shape of a hanging chain, is just y of x being equal to a times cosh x over a. And this is our final answer. And I guess this is quite gorgeous, as we see that a simple differential equation gave us something incredibly valuable. We managed to compute the exact equation of something that we see every single day. It has a mathematical equation all of its own. So yeah, this shows that math is indeed everywhere around us.
Yeah, so Harriet, okay, it's a nice punchline. It's good that there's a name of the function. You wouldn't guess that hanging chains, really might have been the sort of thing where you had to give it to a computer, but somehow this function's got a name already. Harriet's, I'm not going to say calling you out, but Harriet wants to know why it's okay to assume y of 0 equals a. So this step here, where you said, let's just take y of 0 to be a, that simplifies things, right? Because it looks at c equals 0, which in my Desmos calculator would be there. So this set of solutions like this. I guess it doesn't really matter, does it? That if you've got if you know for sure that the position of the bottom of the hanging chain is somewhere else, then you could set c to be something else if you wanted to. You could always do a transformation. We haven't thought about transforming left and right as well. I don't know if there's a better way to phrase that. Can you think of any better way to say that? Or?
Honestly, I think that it's just the fact that we can literally just move our x's wherever we want.
Right.
So the x's are not fixed, only our shape is. So it doesn't really matter whether our shape is here or if it's down here, because it's still the same shape. And hence we can just choose where our x's, where we want to lay our x's.
Yeah, I guess there's this sort of underlying fact that the chain. This all sounds stupid. The chain could be anywhere. It could be here, or it could be over there, or next door, or where you're watching at home. Our equations don't really have a way to capture that translation of where is the chain. So we shouldn't really be surprised when our solution gets out at the end. It's got some translation up and down in this case. It's got some translation. And somehow that's not an exciting fact about the chain. So maybe if we want, I guess I think of this as one particularly nice solution. That all these ones with different values of c in, I guess they sort of exist as well, the different chains at different heights. But we sort of knew that. It was even in your nice answer, a cosh x over a, which is a really gorgeous final answer. Even in that final answer, you've got a kind of caveat that, oh yeah, it might be next door, or it might be upstairs, or it might be moved around. Depends where your axes are, I suppose. So I think, yeah. So an anonymous person has put in chat. We are only looking for the shape of a hanging chain. We don't care where it is. Maybe that's the fastest way to say I don't care what c is equal to at the end. We've got a little bit of time. I think I'd like 5 minutes to try and tell them what cosh is, if that's all right. And then maybe we could do sort of 10 minutes of talking about differential equations more generally, or talking about other things to do with hanging chains, if that's all right. I interrupt for a little bit. My bit of 5 minutes here is really easy. Somebody asked in chat, what is cosh? And it kind of feels like, just for a complete picture, I'm just going to finish up. This is A-level further maths. There's someone in chat who always wants to know what level things are at. This is very clearly, I think, A-level further maths. Let's label it. A-level further maths content warning. So if you're doing A-level further maths, this will come up at some point. Okay, so the idea is we define these two new functions. They're great. They do loads of interesting things. They've got these funny names, which are a bit like cos and sine, but with an H in here. Some people pronounce them cosh or hyperbolic cos or something like that. Or this one, some people pronounce this one shine, as if the H is over here between the S and the I. Some people say cinch. Some people say sinha. But anyway, whatever you're calling them, they've got some nice definitions. This one is this one is 1/2. I was about to say it was the average of these things, just to be whimsical and funny, but that's not a helpful thing to say. It's nothing to do with statistics. It's e to the x plus e to the minus x all over t. And this one is 1/2 of e to the x minus e to the minus x. Well, these are exponentials that you might learn about in normal A-level maths. Maybe you've already seen about exponentials. E is just some number, it's about 2.7. And that's all it is. If you want to differentiate them, then you'll need to know how to differentiate e to the x and e to the minus x, which, if you haven't seen that yet, then I guess there's no way to differentiate these. If you have seen how to differentiate these functions, then give it a go. Work out how to differentiate them. And then there's a bunch more things you can do from there. As soon as you learn about differentiating inverse functions in A-level, you could have a go at differentiating inverse of these functions. To try that out, they've got a... look, Alfie is inventing maths in chat, which I really want to highlight that yes, because mathematicians are brilliant, there is such a thing as tan, with tanch with an H, and yes, it really is defined as shinch over cosh. Which is great, and then it does exactly what you want it to. It's defined like that. They have some nice relationship people are putting in chat, because chat, I forgot to warn you, chat is very, very keen on complex numbers. There is, behind the scenes, a fantastic thing involving complex numbers that people in chat are very excited about. There's a relationship between these functions and the normal cos and sine things that you learn about from trigonometry that involves some factors of I, the complex numbers. Seems pretty good. So somebody, just to wrap up, somebody's put so people are putting relationships that they know about hyperbolic functions. It's clear that some people in chat know about hyperbolic functions, which, okay, a little bit of showing off normally in chat, but hey. And people are very keen on complex numbers. But this question that started, maybe this is a dumb question. Oh, it's gone. Oh, there it is. It started, maybe this is a dumb question, but it's not. If you have an equation with cosh and sine are equal to something, what are sine and cos actually equal to as equations? Right, okay. I've got this nice definition for cosh and sine. Have I got a nice one for sine and cos? The answer is yes. That I've got, behind the scenes, I've got a really nice definition of these cos and sine that you know from things that you know from trigonometry. I've got a nice definition of those, but it involves complex numbers and it involves exponentials of complex numbers. So this is hiding off away from the A-level further maths bit over on this side thing. That's where the complex numbers are hiding over here. That this anonymous person, they think it's a dumb question, but it's not a dumb question at all. Yes, I do have definitions of cos and sine as well. They're very similar, and they involve complex numbers. That is the thing about complex numbers, Harriet, that they're related, just like that. All the equations there, left and right of the double line, are kind of the same equation. Yes, Tia, that is the definition of tanch. Yeah. And fun exercises to try sketching these things. You've seen cosh. You've seen cosh. Now get ready for... I'm going to ruin this. This is no longer going to be a hanging chain. Shine. Looks a bit like that. Oh, I've got a translation on it. There we go. Let's turn that off. There we go. Shine. And maybe homework. You can have a go at working out what the ratio of those is. People in chat excited about other things, a bit like that. Do I need an either? Okay, right, good. Good. Okay. That was my 5 minutes on hyperbolic functions. It's good that everyone's forgotten that 2 weeks ago where I tried to mention hyperbolic functions, and now I've had a better attempt at it. Do you want to tell them anything else about differential equations or solving things like a hanging chain problem?
Sure. So, what I would like us to recall is our initial question. So, we were wondering if there is a similarity between a hanging chain, the way the sound of the strings of a guitar travels, or the position of a single electron particle at a given time. So, well, as you can probably guess by now, from our previous discussion, all of these are modeled by differential equations that we can solve using simple techniques, plus some initial or boundary values, as we have seen earlier when we noted that y of 0 is a or y prime of 0 is 0. And to give you some examples, so for example, the equation of a wave is a second order partial differential equation, and I can write it down, but don't worry about the details too much. So it is d squared u by dt squared being equal to c squared times d squared u by dx squared, where c is just a constant. And to this one, we apply initial conditions u of x0 equals f of x, and du by dt of x0 is simply g of x, where f of x and g of x are just some arbitrary functions that we choose beforehand. And we can solve this to give the specific equation of a traveling wave. And yeah, this is basically what we have for waves. I'm not going to go into more details about it because it gets quite messy. But the idea behind everything is the same as we did previously. And for the other thing, so for the particles displacement equation, the differential equation is even weirder. So it is known as Schrodinger's equation. And conceptually, the Schrodinger equation is the, say, quantum counterpart of Newton's second law that we know from classical mechanics. And given a set of known initial conditions, Newton's second law makes a mathematical prediction as to what path a given physical system will take over time. And the Schrodinger equation gives the evolution over time of a wave function, which is basically the quantum mechanical characterization of an isolated physical system. So this equation looks way more complicated. And I can try to write it down, but I'm not sure if I can manage to get it right, but there's still hope. So it is I, where I is just the complex number I. Then we've got a constant, which is h bar, and it is just a constant. So we literally it's just a constant. It has a known value. And then we've got d squared of our function, which is psi by, sorry, we don't have a second order there. If I can understand how to use Miro, that would be great, but yeah. So d psi by dt is just minus h bar squared over 2m times the second derivative of psi at x plus v of x, which is just potential energy times this function psi. And this is a Schrodinger equation. It looks even messier than the one above, but it can be solved in exactly in quite a similar manner to what we've done previously. And the idea behind it is the same, just differential equations that model real-life phenomenon. And from all of this discussion, we can see that differential equations can do quite wonders, I would say, and they can model loads and loads of real-life phenomena. Their applications are endless, and you encounter them everywhere throughout mathematics and other science areas. They might look overwhelming at first glance, especially if you just look at the Schrodinger equation. But once you understand the method behind them, the possibilities that they offer are incredibly powerful. And yeah, I think that this is quite everything that I wanted to say about differential equations. Yeah.
Brill. I love both of these differential equations. They're very complicated, and we're getting questions in chat, of course, because there's all these different parameters and letters going on. There's some second derivatives. I started drawing an atom to illustrate your Schrodinger picture, and then I realised that that's not how Schrodinger's equation works. So I've had to label my picture not this. So maybe don't ask me for interpretations of the Schrodinger model. I guess the idea is that there's other differential equations that help govern other things. Someone in chat has reminded me. Oh no, I wasn't. Zach has reminded me. Zach in chat has reminded me we have a previous episode about the heat equation, which is another differential equation that describes how heat moves around. I'm pretty sure we did a previous episode about the heat equation. I think Jonah was on at some point last year to talk about heat moving around and solving differential equations over there. Differential's put a link in chat to solutions of this Schrodinger equation. I think steady state solutions for the hydrogen atom. I can't entirely remember how this works. That was evidenced by my picture of an atom. Let's say that we don't have time to explain it now and go there. This is beyond A level, of course. There's no university. Here are some differential equations, but half the game is to come up with a differential equation. Like what are we trying to solve? What's the actual thing we're trying to describe? That at university we explain to people where this wave equation comes from, what it's got to do with waves. So how you might look at waves on a string or something, like a guitar string that you've just twanged. You might look at those waves and come up with something by doing an argument like we did before with forces to come up with a differential equation for how that string moves. It's got time derivatives and x derivatives, and that's not even go there. But we have some story about how we get to that differential equation, and then some strategies for trying to solve it, which is kind of the two halves of the story that we had before. So I think that picture of before of the hanging chain example was actually really good for showing how first you need to make a differential equation. That's half the story. Then we can solve it using maybe some pretty cool math that we've got. There's an H bar, H with a line through it. Did you say what that was? I missed. Did we say anything about H bar?
H bar is just a constant. It basically has the same dimensions as angular momentum, but it is a constant. It literally just has a numerical value, and it is a constant of nature. I think that if you multiply it by 2 pi, you can find it as Planck's constant, and this h bar is just known as the reduced Planck constant. So if you want to look it up, you can just search that. But it is just a constant, so I wouldn't worry too much about it. It's just as we've had previously, we could easily have relabeled it as A to make our lives easier, but it's just known as h bar. So yeah.
I've Differential in chat has just got one of the keyboards that can do it. It's a physics thing. They're much better at coming up with cool symbols for their things in physics. There's a YouTube channel called 60 Symbols, I think that's the name of the channel, that goes through physics symbols. Physicists are really good at coming up with cool symbols, like H but crossed out. Great idea. The best bit is that H bar is just equal to a different physics constant that they already had called H, but divided by 2 pi, which some people call tau. So you can have a lot of fun with this. If bar just means divide by 2 pi, then you can invent some new notation. So sometimes you might want to write 1 over 2 pi, and physics gives you a great way to write that. You just write 1 bar, and maybe you could save some effort like that by doing just 1 bar. You might need to write actually 2 pi, which would be alright. That's just 1 over 1 bar, or bar over 1 bar 1. Anyway, never mind. This notation is kind of pretty weird. Nobody actually uses it for 1 bar. Goodness me, never obvious whether the jokes are landing or not. And it's really dangerous if they don't. Zach wants another video about topology, and which is not out of the question. We're doing another season of these. We've got season 4 coming up. The schedule is going to be, we've got 1 more episode next week, then we're taking a 2-week break for the holidays, and we're coming back for another 13 episodes of season 4 of the Maths Club. Get excited for that. Very redundant yet cool simultaneously. That can just go. That's like, It's too long for my number plate, but maybe it can be my like CV header or cool yet redundant. That's the only thing we want. I think we're wrapping up, but anything else we want to add at the end?
Not really. Just I really hope that you enjoyed this and that you found something interesting that you maybe want to pursue further. And yeah, if you choose to do maths at university, then you will encounter these things almost every single day. But they're actually quite fun. And once you get a hang of it, and you will in your first year, like definitely, they're quite fun and they're incredibly useful. So yeah, I really hope that you enjoy them.
Thank you very much for coming on the show. Thanks for showing us different equations and shapes of hanging chains. Never going to look at these paper clips in the same way again. And thank you for watching. We're going to be back next week for one more episode in this season of Oxford Online Maths Club. I think next week it's just me, but I'm actually going to talk about fluid dynamics, which I've been threatening to do for ages, but actually talking about fluid dynamics properly next week on the Oxford Online Maths Club. We'll see you there. Have a nice evening. Have a nice week. Bye. How do I turn it off? There. Bye.